A very warm welcome to all of you. Myself Rajan Choudhary, Professor in the Department of Civil Engineering, Indian Institute of Technology, instructor for the NPTEL MOOC course Pavement Construction and Technology, funded by Ministry of Education, Government of India. Today's talk will be a part of the lecture 6, Characterization of Materials for Use in Pavement Subgrade, under the module 3. At the very beginning, I would like to acknowledge the use of text, information, graphs and images sourced from various standards, textbooks, journal articles, reports, newsletters and public domain searches. So, when it comes to the pavement subgrade construction, one important aspect one wants to know is when you are compacting any soil, you require to know what amount of water is to be added so that you can, for a given compactive effort, you can achieve a good density out of it. So, the relationship between water content and the density of a soil is very important, and the density of the soil under a given compactive effort changes with the change in the moisture content. So, if you are going to prepare a bed of a soil under the construction of a subgrade, you need to know how much amount of, you can see there is some sprinkling of water which is going on. So, you need to add the adequate amount of water, you need to mix this water with the soil, and then you need to compact it to attain the density. So, it is important to determine the right amount of water known as the optimum moisture content, and it is very commonly referred as optimum moisture content. The right amount of water content for a given soil is crucial for effective soil compaction in the field, because you need to attain a targeted density. The density is important. This ensures efficient compaction and helps us to predict the maximum density the soil can achieve at that moisture, and we want to know how much is that maximum density which is achievable at the optimum moisture content. So, optimum moisture content itself is the moisture content which gives you the maximum density. So, there are two terms, one is optimum moisture content and corresponding to it we have the maximum density, and the density which is referred is the maximum dry density. So, you will very frequently see the two terms used as optimum moisture content, and second is your maximum dry density. Now, for this particular one, at the laboratory scale, you need to have a test which can help you to determine the degree of compaction achievable, that is the density achievable at a given water content. So, you can try with different water content and see for a given compactive effort how much density is achievable, and then you will, from that density water content curve, you will try to get the optimum moisture content and the corresponding maximum dry density from this particular relationship. Now, the test or the coded provisions which are followed for this particular one is IS 2720 part A and IS 2720 part 7. The difference is specifically in terms of the compactive effort which is used. The IS 2720 part 8 says method of test for soil determination of water content dry density relationship using heavy compaction, and the other one says it is using the light compaction. So, it is the compactive effort in which they mainly differ, the 2720 part 8 and part 7. So, this particular test helps us to determine the optimum moisture content and corresponding maximum dry density which is worked out. For most of the highways, we look for the determination of optimum moisture content and maximum dry density as per the heavy compaction. So, it stipulates the method for the determination of the relationship between the water content and the dry density of soils using light and heavy compaction. So, if 7 and 8 both are there, so you can see what you require normally for doing this particular test at laboratory. You will have these cylindrical molds with you of different sizes. They can be of 10 centimeter dia, 15 centimeter dia. You need to have a compactive effort which will be in terms of different rammers for heavy compaction. This particular test is very frequently referred as a Proctor test also. So, if there is light compaction, we call it as standard Proctor test, and if it is heavy compaction, we call it as modified Proctor test. So, in heavy and light compaction, one major difference will be in terms of the rammer weight. So, it is the compactive effort which is going to vary, and the height through which this rammer is allowed to fall. In this light compaction it is 310 mm, and in heavy compaction it is 450 mm. Now, here this table again shows a comparison. You have a soil sample. Depending upon the sizes of coarse particle present in a soil, you can use smaller molds or you can use bigger molds. Bigger molds will have, with a 15 centimeter dia, will have a volume of around 2250 ml, and the smaller one will be having around 1000 ml. Now, this particular one, when you are using, as I said, for our cases we will specifically prefer for heavy compaction only for most of the highways. So, in that case you can go with 1000 ml mold or 2250. So, this will be 10 centimeter dia mold and this will be 15 centimeter dia mold, cylindrical mold of this type. This is a collar, the top which you are seeing, this is a collar, and the bottom is one your cylindrical mold, and these are the different rammers which are going to be used. Now, when you are going for this heavy compaction, one important part is you are going to compact the soil in 5 layers. So, each layer you will take an approximate quantity depending upon the mold which you are using, which is stated in your IS 2720 part 8. So, depending upon the mold size, whether you are using 15 centimeter one or 10 centimeter one, you will take initial weight of the soil and then add the starting water content to it. You will compact it in 5 layers. Each layer you will give, when it is the smaller dia mold, 25 number of blows. When it is the bigger size of mold, you will give 55 number of blows, so that your compactive effort remains same and the rammer weight is also same in both the cases. So, this is how you compact this particular one, and at different water content levels you determine the density of the soil sample in these molds. And finally, what you get out of it? You get a curve between your density and the water content. So, the density which you get out of this particular measurement is your wet density, and the density which finally is used here is your dry density, which will be your wet density plus your water content divided by 100. So, what we refer here is the dry density. And so, the curve of dry density is drawn, and then you are going to see the moisture content at which you get the maximum dry density. So, this moisture content will become your optimum moisture content, and this will become your maximum dry density. So, this what you want to see, that for a given compactive effort, heavy compaction, what density can be achieved at maximum density achieved, and what will be that water content. So, this is important. Now, while reporting this particular value, it is always suggested, if that your moisture content is less than 5%, you can round off the value to 0.2%, and if it is between 5 and 10%, your moisture content for your OMC is between 5 and 10%, you can round off to 0.5%, because this plays a major role, because the amount of soil which is to be compacted is very large in quantity. So, even to the decimal places it plays an important role, and if the water content is about 10%, it can be rounded off to the nearest whole number. Now, in addition, under this particular test, there are few important observations which is to be taken care. As I mentioned, your particle sizes may be, your soil may have some coarser particle sizes. So, that you are going to check by using a 19 mm or a 20 mm ISC. Now, if the coarser particles are around 4 to 5%, up to 5%, so around 5% particles are higher than this one, this can be worked out. This you can go with the using the 10 centimeter dia mold, 1000 ml mold in that case. If the particles are bigger than this one, because in this test you will use all material which is passing this 20 mm sieve or 19 mm sieve. Now, if there is a significant proportion of particles which are retained over this one, then it is better to use for your molds which is having bigger sizes. So, we will prefer to use molds of 2250 in that case. So, for soils containing larger proportions of gravel, the use of bigger mold is advised in this particular case. Along with it, you need to know that what first of all, one important thing is at what content you have to start, and then finally what increments you have to give in that case. Each increment will be there from one water content to the second water content, what increments. So, one is at the commencement of the test what water content is required. So, normally for different kind of soils the requirement of water to get the maximum density will be different, but for a starting point, a guideline, it says that if you have a sandy and gravelly soils, the moisture content of 4 to 6%. So, you can start first at the level of say 5% moisture content, and then you can give an increment over it. This increment can be possibly 0.5% for sandy and gravelly soil, and can be more in case of your clay soil. And if there is a cohesive soil, that is the clay content is more in that particular case, you definitely you will have a higher demand of water content. So, higher value of optimum moisture content you. So, if you start at 5%, you have to do multiple tries. So, it says that you should, it is better to start in the range of 8 to 10% if you have a cohesive soil. And it says so it says 8 to 10%, sorry, it says 8 to 10% below the plastic limit of the soil. So, if the plastic limit of soil is say 20, I will go around starting say in that particular case 10 to 12% will be my moisture content at I will start. If my plastic limit is 30, I will better to start at say 22 or 20 initially starting. So, this plastic limit plays, so that is why we do the determination of Atterberg limits to know the, before we proceed with this Proctor test or the test to determine the water content and density relationship. So, it says with cohesive soil a moisture content about 10 to about 8 to 10% below the plastic limit of the soil is usually found to be suitable. Now, other important aspect is when you are using a clay soil, normally you are doing a hand mixing. So, there it takes time. Clay soil, a uniform dispersion of the water normally takes more time. So, in that case, if you do very quickly, the water may not uniformly distribute among your soil mass which you have taken for your test, and that soil mass quantity will depend upon the size of the mold. So, it says if such a case is there, you are experiencing that uniform mixing is not there. So, in what it says, the mixed sample may have to be stored in a sealed container for about 16 hours for the testing, especially when plastic clays are there. So, hand mixing may not be good enough. So, you need to store it so that the water is absorbed by the soil mass in this given amount of time, and then you do with this compaction procedure. Here you can see this the own dry soil mass is there, then water is added to this particular one, uniformly mixed. Thereafter, you give a definite quantity of it to it, you will compact it in 5 different layers, giving different amount of compactive effort. The procedure, the detailed procedure is already given, very well explained in IS 2720 part 8. And then finally, you trim out the extra material, and this is there. You will take the sample of soil for your moisture content determination, and for this particular one mold, you will take the mate with the wet soil plus the mold plus the base plate and the empty mold and the base plate. So, you get the wet mass of the soil. So, from the wet mass of the soil and the volume of the mold, you get its wet density. And as I mentioned, once the wet density is there, you can work out your dry density using the wet density plus your water content divided by 100. So, this gives you your dry density which is required for this density moisture relationship. And as I mentioned, how much increments? If I start, say there I started for sandy and gravelly soil at 5% moisture content, and I started say for the clay soil having a plastic limit of say 20, so I will start say around 10% of water content. Now, what increments I will go here? I will go here increments of either 1 to 2% in case of sandy and gravelly soil. So, next may be say 7% or 6%. And in case of the clay soil, because it may go to higher values, so I will go for say 10 to 12%. So, here I can go for 1% increment in water level, and in clay I can preferably go for 2% increment in the water level. Now, Once you get this maximum dry density and moisture content, there is again a requirement which is given for the suitability of a soil to be used in different applications. It says, the MORTS 2013 says, if you are constructing an embankments up to a height of 3-meter height and which is not subjected to excessive flooding, you can have a soil which should not have a maximum dry density of less than 15.2 kN per cubic meter. So, it will be 1.52 gram per cc. So, the density should not be less than 1.52. And it says, if the embankments, if you are using it embankments of height exceeding 3 meter and which may be submerged to water for a longer period of time, then the density should be at least 1.6 gram per cc. And it says, if you are using it for subgrades and for earthen shoulders and backfill materials, then it should not have a density less than 1.75. So, once you have this relationship arrived for the soil samples, then preferably you will come to know whether it is suitable for which kind of application, whether it is suitable for my subgrade construction or earthen shoulders construction or not. So, this is another aspect which you arrive after this particular measurements of the Proctor test. And once you have this density with you, optimum moisture content, and then the soil is constructed using that moisture content in the field. So, while compacting it there in the field, it is said that you need to go for compaction which is at least 97% of what is achieved in the lab. So, it says relative compaction as percentage of maximum laboratory dry density, because it may not be always possible to attain what we have in the laboratory, but at least a good amount of density is achieved. So, it says that the subgrade material or the other shoulder material should not be compacted less than 97% of their density. When it comes to embankment, it says it should not be compacted less than 95% of the maximum dry density you got from the heavy compaction Proctor test or the modified Proctor test. And even it says, first of all, expensive clays we discussed in the previous lecture, it should not be used in subgrade as well as for the 500 portion just below the subgrade. And if it is remaining part, if it is used, then the density can be in the range of 90 to 95% while preparing these particular below layers of a pavement structure. Now, once this is done, the other parameter which is important to know the characteristics of strength or the characteristics or the specifically the strength of the soil to be used as subgrade is California bearing ratio. Now, this is an index property. This is an index which is used to evaluate the strength of the subgrade and also of granular materials, and this particular the index which is measured is used in the design of flexible pavements. Now, what is this? This is a penetration test. You can see from this particular one, there is a cylindrical mold, there is a soil sample here, on the top of it there is some surcharge weight plate is placed, and then this plunger is inserted, is penetrated into this soil mass. So, there will be a resistance to this penetration, and we will measure how much load is required to give a given amount of penetration. So, it will be a plot will be generated between your amount of penetration and the load required for that given amount of penetration. So, you have this dial gauge to know the penetration, and you have this load cell to know the load which is required for that given amount of penetration. So, and there are the requirements which are mentioned for this particular one, specifically how much amount of surcharge weight is there. So, and the sample which is to be used for this particular one is the one which is prepared using the optimum moisture content and the maximum dry density. So, it refers, CBR is referred as the percentage of force per unit area, that is the pressure which is required to, because this is a dia of 5 this plunger is having a dia of 5 centimeters. So, we can work out the area for it. So, the load divided by area will give you the pressure. So, it says the force per unit area required to penetrate a soil mass with a circular plunger of 50 mm diameter, and this rate of penetration is also fixed. It says 1.25 mm per minute rate of penetration should be there in the soil sample. And then what we need to work out? We need to work out the pressure confirming a penetration level of 2.5 and 5 mm. We will go for penetration up to 12.5 and more than that, but what we require for working out the CBR are the penetration levels of 2.5 and 5 mm. Now, this particular detailed procedure of CBR California bearing ratio determination is given in your IS 2720 part 16. Now, as I mentioned, this gives you a curve between your load, which is in terms of pressure, and the penetration. So, initially in some of the cases you may get this kind of curve which is shown here, but the one which is expected is to be in this particular form. This is what is expected. Now, here you can see the slope of the curve is initially in this form. Now, this slope needs to be corrected. Here you can see a good amount of it shows penetration occurred without taking much load. This possibly happens initially if the top surface is not well compacted, or there is a good there is not a good contact between your plunger and the soil sample. So, you need to make a correction for this slope. So, here if you in this particular case you can see the correction is made and you start your penetration reading considering this as the 0, and in this particular case there is no correction which is required. So, this load the penetration and load curve needs to be looked whether a correction is required or not required, and then you are going to see the load corresponding to 2.5. Here once the correction is applied, so this value will slightly shift on this particular side considering how much shift is there on this side, and here in this particular case in this one there is no correction required. So, you will be looking for this particular value and you will be looking for this. Now, this value have to be compared with the load which can be taken by a standard material. So, it says that the CBR of the subgrade soil which is required for the design of new pavements as per this particular one, and another aspect which is to be taken care is this soil, this penetration of the plunger in the soil can be done after submerging the soil sample in water for 4 days. So, it can be a soaked CBR or it can be an unsoaked CBR. Normally, what we try to do out of soaking this particular sample in water is we want to create the worst situations which can be there. A soil when if the subgrade gets completely flooded, which is not what you will actually allow in practice, but then also for the worst scenarios we are considering that the soil is in completely submerged condition. So, we are going to, and at that condition how much is the strength of the soil. So, for that we will determine the CBR after soaking this particular soil sample in water for 4 days, and this will be our soaked CBR. And as I said, while compacting this soil sample in this particular mode, again you have to compact in 5 layers, you have to give heavy compaction. That particular process is again stated here. You can go for static compaction also, you can go for dynamic compaction. Static compaction is preferred because once density and water content is known to you, you can choose the considering the volume of your mold, you will pick up the soil weight and then you will apply a static load, compact it within that particular volume, so that you get the adequate amount of the right amount of OMC and the corresponding MDD for soil. Now, here it says when compacting this particular one, you will compact it to 97% of your MDD. So, this is an important percent, that minimum when you go that at a placement density minimum 97% of your Proctor density which you have arrived in the earlier test. Now, once this, so you get the value at 2.5 mm penetration, you get the value at 5 mm penetration. Normally, most of the time you will get higher values at 2.5. So, you will prefer to choose this particular one, and then what is there, what you get from the load penetration curve divided by the standard load. So, this standard load is 1370. So, and for a 5 mm penetration, this standard load is 2055. So, your CBR, what CBR says, it is the load taken by a sample specifically at 2.5 mm or 5 mm penetration divided by the load taken by standard aggregates at the same penetration levels. So, if 2.5 is considered, then 1370 load will be considered. If 5 mm is considered, 2055, and this will help you to determine the CBR of it. Now, soaked CBR may not be always required, because there may be certain regions where rainfall is very less. So, there if we are going to work out soaked CBR, we are underestimating the soil subgrade strength. So, in those cases we may go for unsoaked CBR determination also, but otherwise for other cases we will go. So, it says in areas with less than 1000 mm rainfall, 4-day soaking may be too severe condition, because then if your subgrade strength you are considering quite low, then the crust is to be increased. Now, in addition to this determination, once you get this particular determination, you because the subgrade has to be constructed along the entire length of your pavement. Now, for this particular one, you will require a good quantity of soil. So, you may either use the existing soil or you may select a borrow area. Now, for that particular borrow area, you have to work out the CBR of that soil at for those particular, and the soil may vary from source to source, and it may be different in the first 10 kilometers, may be bit different in the next 10 kilometers. So, you have to work out the CBR if this depending upon how much variation you are observing in the soil sample, and for each sample you have to do multiple samples for it to determine the CBR value. And it says that once you are having, say for the entire stretch you have the CBR values with you, it says specifically for roads carrying traffic less than 20 MSA, 20 million standard access, the 80th percentile CBR value is recommended. That means, in any case when you do the testing, only 20% of the results of CBR values may fall out of it, or maybe below this. In rest of the cases, 80% of the results of CBR, if you do a cross examination, should be more than that particular one. And for higher categories of roads where the design traffic is more than that, it says if it is more than 20 MSA, I will go for 90th percentile of CBR, because I may have say 10 CBR values depending upon the different type of soils which are available for me to construct. But I'll not vary my pavement crust from section to section or length to length. I'll keep my pavement crust more or less uniform. So, I'll pick up one subgrade CBR value to design my pavement crust, and that says if the traffic is more than 20 MSA, go for the 19th percentile of your CBR from whatever the results you have got. Now, this while making the computations for the pavement crust determination, the input has to be in terms of the resilient modulus. Now, this is again a parameter which gives you a strength in terms of the strain applied. Now, resilient modulus, for determination of resilient modulus of any soil sample, you need to make use of the triaxial test. So, this triaxial test. Now, from this triaxial test, normally stress is applied and strain is measured and resilient strain is measured. So, you get a resilient modulus, and that resilient modulus is used in the design of flexible pavements as per IRC 37/2018. But in most of the cases, it is time consuming. Many of the labs doesn't have this particular facility. So, there are certain empirical relationships which are available and given by the IRC 37 itself, which says if the CBR is less than 5%, you can estimate the resilient modulus as 10 into the CBR value. So, because while making the computations for flexible pavement design, you will require the resilient modulus value. So, in lab you have determined the CBR, then you will check whether your CBR is less than or equal to 5, you will multiply it 10. So, my CBR say 6 is there, then my resilient modulus value will become 60 MPa. Or if my resilient, this particular one CBR value is say 8%, then I will multiply it by 17.68, whatever the value comes out, this will be my resilient modulus, and this resilient modulus, which we will call as MR, will be used in the flexible pavement design procedure. So, this is another important aspect, and some of the laboratories which have the facilities can directly determine the resilient modulus values using the triaxial test. Then they do not need to use this empirical relationship. Now, another concern which arises is whenever these subgrade soils are constructed, one case may be there, whatever soil you are using in embankment construction may be quite different from what you are using in subgrade construction. As I mentioned, in the embankments, the requirement of density is different, the requirement of density while you are constructing a subgrade is different. So, if there is a significant difference, if I am between the layers which I am constructing, or even there may be a possibility that since I am doing my subgrade construction in multiple layers, because if I am doing a subgrade construction of say 50 centimeter, I will not be able to do in one layer, I may be doing it into two to three layers. Now, in each layer, say suppose I constructed my subgrade first layer of a thickness of say 150 mm, second layer also of a subgrade thickness of or I will construct it say the bottom one with a thickness of 200 mm, this the second one of 150 mm and the third one of again 150 mm. So, this gives me my 500 mm. Now, the soil which I have used in these first two layers is the same soil, but what I finally got for the third layer is much different. The CBR of this particular soil is much different by the underlying layers, because here I used one boro area, here I used the third. You will not prefer to do it, but still there are limitations which exist in the actual field. So, in that case you need to work out the effective CBR for this particular one, that what this combination will give you the effective CBR. So, the IRC 37, which makes use of the software of IIT Pave, I am not discussing that particular part here, because this is the design aspect. So, here the important thing is that gives you I will briefly mention in the next slide, that gives you idea how you can work out if there are 2-3 soils with different CBRs. So, what will be the effective CBR which is to be considered? Once effective CBR is known to you, you can work out the MR for that particular one, and then that MR has to be used. So, even there may be a case that your subgrade is very good, the 50 centimeter of subgrade is very good, having a CBR say maybe of 12%, but what below is your embankment is quite weak. Maybe having a CBR of say only 5% or maybe less than that. Then again this needs to see that what should be the effective CBR is to be considered, because this layer is going to be resting, and there may be otherwise case also, there may be some rocks may be there, a rocky strata may be there over which you have constructed. In cut areas this may happen. So, then the effective if I consider the CBR of the rocky strata, it will come out to be very high. So, I do not consider, in that case I will go with the CBR of this particular soil only. But when it is weak, for my factor of safety I will work out the effective CBR. So, it says that the design should be based on the effective modulus or CBR value of a single layer subgrade, which is equivalent to the combination of the subgrade layers and the embankment. So, you need to work out the effective CBR, which is a combination of the different layers of subgrade or the subgrade plus your embankment, and this particular effective procedure is given in IRC 37. This is important to note that this is to be done. And another aspect which it says that the effective subgrade CBR should be more than 5% for roads carrying 450 commercial vehicles per day. So, there is you should not construct roads having subgrade soil CBR less than 5% if the amount of traffic which is coming, commercial traffic, is the one which have the laden weights more than 3 tons. So, now as I mentioned, IIT Pave, the flexible pavement design IRC 37 works, gives the software IIT Pave for working out the different crust compositions. And under this particular one, it gives that if you are working, as I earlier mentioned, that if we are doing on a rocky foundation, may be larger than however only the CBR of the borrow area will be considered. Even if rocky strata is there, I will not consider an effective CBR to be more than what which is. But if it is below 1 is a weaker one, then I will work out for the effect. So this keeps my structure, to keep my structure safe. And as I said, but when rocky strata is there, normally the problem with pore water pressure comes up. There is the water which is there exists between subgrade and rocky strata, creates a pore water pressure, which we discussed that this will lead to the loss of the shear strength of the soil. So this needs to be adequately checked, especially that there is some drainage option is there, that pore water pressure is released. And another important aspect, as I said, when you are working out how you worked out, a simplified version is that if I want to work out the resilient modulus of a single layer, what it can be done, I can consider here it is given bituminous, granular and soil subgrade. I can consider it in a different manner. I can consider it in a subgrade layer 1, subgrade layer 2 and an embankment layer. So with this particular combination, taking a standard load which says, this is as per IRC 37, it says you consider, you work out this the effective resilient modulus by considering a contact pressure of 0.56 megapascals. This is your contact pressure, and corresponding to this contact pressure you work out the contact area. This is for the wheel load which is going to come. I am trying to work out the effective resilient modulus, and here it says that if what should be the radius of circular contact area. It says radius of circular contact area, which can be calculated. The load which is to be considered is 40 kN. It is because considering a standard axle load of 80 kN. So there we are considering the single wheel load of 40 kN and the contact pressure of 0.6. You get a value of area of contact area as 150.8 mm. So with this particular one, once you through this IIT PAVE software, if you are able to, you work out the deflection, and using that deflection value and the contact pressure and contact area, you get the value of your resilient modulus. So this is as per, this is another one step higher to see what you get. So this combination you can work out directly to get your resilient modulus for this particular combination of different layers. And finally, it says whether you go by the expressions, empirical relationships which were given to correlate your MR with the CBR. As we have seen, if it is CBR is less than 5, less than equal to 5%, MR is 10 into CBR value. Now for this particular cases, even here also it says, so this will come out to be, say, your, if CBR is your 5, so MR value will be coming out to be 50 MP. Whatever cases it is there, it says that for the design purpose, the CBR or the resilient modulus should be limited to a maximum value of 100 megapascals only. So in flexible pavement design, when you arrive to these particular combinations for a limiting safety aspect check, it says that the maximum resilient modulus of a subgrade layer can be considered as 100 megapascals. So this gives you a description about the different characterization which is required for doing the flexible pavement design computations in respect of the subgrade soil. Thank you.